start just though by saying that none of what I'll be showing would have been possible without a lot of work from a lot of people, only a few of which are actually mentioned here. So big thanks to the ICON team. So I'll start with a little bit of background on thermospheric dynamics, but then jump right into showing, introducing the ICON mission, as well as focusing on MIGHTY, which is one of the 4 instruments on ICON. I'll show some data from MIGHTY, both the temperature and wind data, and then talk a little bit about our initial efforts at ground-based validation, so comparisons with similar ground-based instruments. And then, depending how much time is left, I'd like to spend a few minutes talking about some of the initial science results by actually combining different instruments on ICON with a focus on electrodynamics. Okay, so most of what I'll be focusing on today is with respect to the thermospheric wind, or the motion of the thermosphere. That's altitudes from around 85 kilometers up to 500 kilometers, where the exosphere begins. So the thermospheric wind it really plays a key role in the dynamics and energetics of the whole ionosphere thermosphere system, regulating energy transfer from above and below, between day and night, and between the neutral part of the atmosphere and the ionized part of the atmosphere, the plasma. So, you know, it's, to me, intrinsically interesting, but even if you don't care about the thermosphere at all, I'll argue that to understand ionospheric variability, you have to first understand thermospheric variability, because even here at the peak of the ionosphere, the peak of the F region, which is the densest plasma in geospace, the neutral atmosphere is still 2 to 3 orders of magnitude denser. So the main motivation of ICON is to understand ionospheric variability. So for those that aren't aware, you know, since the ionosphere is produced by solar radiation, you might expect that the daily cycle of the sun rising and setting would be reflected in a continuous daily cycle of ionospheric density and altitude. But observations suggest that's not the case. So the ionosphere varies from day to day in a way that can't be explained simply by solar radiation. So what I'm showing here is an oversimplified picture of what we know about ionospheric variability and how it's influenced from above, geomagnetic activity, and below, tides and waves. So we've known for a long time about the fact that during periods of strong geomagnetic activity, energy and momentum inputs in the high latitudes can make their way down to the lower latitudes and affect the thermosphere and thus the ionosphere. Something that's been a growing realization in the past maybe 10 or 20 years has been the influence of the lower atmosphere, of weather, you might say, on space. And that can happen either by direct propagation of lower atmospheric waves up to the thermosphere, where they then have an effect on the ionosphere, or through the dynamo mechanism. So waves that only make it up to the lower thermosphere can impart patterns on the ionosphere via the dynamo. And we'll focus on that a little bit later. So throughout all of these mechanisms, except the penetration electric field, the thermospheric wind is really a key observable. And that's one of the focuses of ICON, one of the instruments on ICON is MIGHTY, which observes the neutral wind. The problem, though, is that unlike the ionosphere, which you can bounce radio waves off of, the thermosphere is rather difficult to observe. Most of the action in the thermosphere happens a bit too low for satellites to fly through it in situ and make in situ measurements. It's a bit too high for balloons and aircraft. But luckily, the thermosphere provides us with these naturally occurring airglow emissions. Here's a picture. This is just a visual wavelength picture taken from the space station. And you can see the red line emission here at around 200 to 250 kilometers altitude, and the green line emission here around just under 100 kilometers. This is a picture taken during the night. During the daytime, both of these layers get wider. So the idea here is that as the atmosphere moves, that imparts a Doppler shift on these emissions, that with a high resolution interferometer, you can actually measure that Doppler shift, and that's a proxy for the motion of the thermosphere or the thermospheric wind. So as I mentioned, the wind is a key observable for ICON, which has as its primary goal to understand the source of ionospheric variability. So both understand the mechanisms and how those mechanisms compete from above and below. And that maps to the three science goals of ICON. Focusing on MIGHTY, MIGHTY provides the horizontal neutral wind vector profiles, so actually altitude profiles, from about 90 to 300 kilometers altitude. And it uses the Doppler shift of these, the red emission and the green emission, to measure the wind. And it also has measurements of the oxygen, the O2 A band emission, the infrared emission, to measure the temperature. And there's two sensors on MIGHTY. It's MIGHTY A and MIGHTY B, which I'll go into. Here's just a picture of the ICON payload, and these are the two MIGHTY instruments. The optics here and the big radiators. Here's MIGHTY A and MIGHTY B are the two. You can see both of them here. And this is the PI of MIGHTY, Chris Englert. Here's just a picture of the fully integrated ICON satellite. It's actually upside down, so the instruments are here on what is the bottom, looking out onto the horizon. Here's MIGHTY A and MIGHTY B. Here's the IVM, and the two ultraviolet instruments are harder to see here. But there they are. So it feels like it just happened, but it was really almost a year ago that ICON launched, October 10th, 2019. It was a Pegasus launch. If you don't know about Pegasus, it's ICON is here just in the tip of this rocket. The L-1011 spacecraft, or L-1011 aircraft, goes up to cruising altitude and drops the rocket, which then launches. And it inserted us into a nearly circular orbit at about 600 kilometers altitude, and right at the inclination that we expected, 27 degrees. So getting a little bit, I won't go too much into instrumentation in this talk, but I'll give a little taste. MIGHTY is, at its core, just a type of Michelson interferometer. And Michelson interferometers are fairly simple in that the signal that you measure is a scaled version of the Fourier transform of the spectrum. So if you have a emission, which is like a Gaussian, that represents the atmosphere at rest, when that emission is Doppler shifted, you think of the Fourier transform property that a translation in one domain is a modulation in the other domain. That just makes a different spatial frequency in the signal that you measure. So as the wind goes back and forth, you can just watch this fringe pattern sort of come in and out. Here's a picture of the interferometer, which is the heart of the MIGHTY instrument, and just show that when you shine a laser pointer through a delta function in wavelength, you get the fringe pattern here at the output. So this is actual data in false color, but it is actual data. MIGHTY A is on the left, MIGHTY B is on the right. And what you can see here on the left is measurements of the green line. This is looking out onto the horizon. So you can think of this as just a picture of looking out at the horizon at the green line and red line, but superimposed is this fringe pattern. So the green line here, the red line here, this is from 90 kilometers down low up to 300 kilometers during the day. And the bottom part of the red side of the image is replaced here with the infrared, the O2A band filters. So MIGHTY is not the first instrument to do something like this. There's successful wind measurements from DE2. There's an FPI on there. On URs and Hardy. Sorry, on URs there was Hardy and Windy, which were wind instruments using a similar observation modality. And then on time there was Tidy. But MIGHTY has the advantage that all altitudes are sampled at the same time. You don't need to scan on the horizon. And Also, all three of these channels are sampled at the same time, so there's no duty cycling. You could get red and green at the same time. As I mentioned, there's two MIghty sensors. That's because each one only gives you the line of sight component of the wind, the Doppler shift along your line of sight. So MIghty A will make a measurement at some remote location, and then about 5 to 8 minutes later, MIghty B, which is mounted 90 degrees apart, is in a position to make a measurement at the same place to resolve the actual vector component of the wind. So the northward, or we call meridional wind, or the eastward, which is called the zonal wind. So in this talk, I'm going to be mostly focusing on the wind, but MIghty also measures temperature, so I'll say a few words about that. The underlying idea here is that the shape of the O2 A band emission depends on temperature. So here's the example of what that spectrum looks like for different temperatures. If you were actually able to fully resolve it, we don't actually fully resolve it because all you need is 3 of these filters at 3 narrowband filters spaced at strategic locations in the spectrum, as well as 2 off-band filters to characterize the background. So as the temperature changes, you can watch the ratio of intensity in these 3 filters change and then infer the temperature from that. So right now we have provided temperatures from 90 kilometers to 105 kilometers at night and 15 kilometers during the day. Okay, so let's look at some data. So what I'm showing here is just one orbit of temperatures. In fact, this is just a dayside pass. So the spacecraft is, well, actually, this is the tangent location, which is the location out on the horizon that MIghty's looking at. So the tangent point is traversing from over North America, across the Atlantic, over to Africa. And it makes a measurement every 30 seconds during the day. So we have many tens of profiles across this dayside pass. Those temperature profiles are shown here in black. And for context, shown here in red are the MSIS 2.0 profiles at the same place and same time. Just to show that the MSIS 2.0 sort of falls within the envelope of MIghty measurements, though of course the MIghty measurements are much more variable since MSIS is only a climatology. This says submitted, but actually as of yesterday it was published, so this is available now. Showing this in a slightly different way, this is the same data but just shown as a function of altitude and time across that dayside pass. Again, just to show that give an idea of some of the small scale structure that MIghty is seeing that doesn't show up in a climatological picture. So there's really an incredible amount of variability here. Okay, getting back to winds, this is a similar plot just showing one orbit of wind data. And here I'm showing day and night. So this is a full orbit going from midnight across the dawn terminator into the day side, where of course we get more signal, so we have a larger range of altitudes that we observe, and then back into the night side. The top here is the red emission spanning from about 150 to 300 kilometers, and the bottom I'm showing the green emission from about 90 to around 200 kilometers. And on the bottom here is not MSIS, but the horizontal wind model 2014, which is another climatological picture. So by and large, MIghty is observing the same large-scale features that are seen in the horizontal wind model, which is based on decades of previous measurements. But again, there's a significant amount of variability, some of which are these disturbances that you can track that seem to be the same in the green line and up into the red line. So that's really exciting. Okay, before showing more data, I'll just give a quick aside about atmospheric tides. So I'm sure most people here are aware, but for those that aren't, tides are the normal modes of an atmosphere. They're a useful basis function to talk about our measurements. And that's because they're the eigenfunctions of excuse the eigenfunctions of Laplace's tidal equation. So what's shown here is a monthly climatology of the tides observed, the average tides observed during, I think it was month of October, by timed. So this is based on tiddy winds and Sabre temperatures. A little bit about the nomenclature. There's a wide spectrum of waves here. The ones that have a phase speed, an east-west phase speed of 360 degrees in 24 hours, we call migrating, because they, from a point on the Earth, they look to be just following the sun. These are waves that are directly driven by sun, so the solar radiation. So other waves we call non-migrating or stationary, and are either have to be due to other influences, either tide-tide interactions or influences from below, like weather, meteorological influences from below. So the point here is that even though not every variation we see is tidal, if you can get the tides right, you can understand a significant part of the energy and momentum coming up from below. So this climatology I mentioned used timed tiddy winds. Icon has a shorter precession cycle, so it would be able to fill out the latitude and local time structure in a shorter amount of time. And MIGHTY observes up to 300 kilometers with slightly better precision. So just to show what a day of data looks like, this is 1 day of MIGHTY east-west winds. Each row here is an orbit, and it's organized in this way because there's 15 orbits in a day, and each orbit tracks a similar trajectory in latitude and local time. You know, of course, when you complete an orbit, you're at the same local time by definition, and you come back at the same latitude, but at a different longitude because the Earth's rotated under you by about 24 degrees. So the point is, if all the structures we're seeing were simply migrating tides, then all 15 orbits would look the same, but they don't. There's a significant amount of variability here, and it's shown just from orbit to orbit. You know, sometimes there's these shear layers, like this incredibly strong 150 meter per second shear layer that just shows up for a few longitudes, and sometimes there's small scale structure, etc. I should mention one thing. There's a big bite out here due to the South Atlantic anomaly. When the spacecraft goes over the South Atlantic anomaly, the radiation environment is too harsh to really make trustworthy measurements. Okay. Just to show this kind of different sort of way, I just took data from one altitude. This is around 110 kilometers. And on every pass, I just plotted a few points around that location up here at mid-latitudes. And the black dots are the zonal wind at that longitude. So, you know, for this sort of analysis, to understand longitudinal patterns at a given local time, you don't need to do any averaging hardly at all. The longitudinal pattern can be observed every day. And what this shows is there's a significant amount of longitudinal variability that we see in the winds, even down in the lower thermosphere. This rivals the strength of the migrating tide, and of course doesn't show up in climatological models that don't have non-migrating tides. So clearly there's a large-scale structure here that's probably a large-scale tide, but there's also variability on smaller scales that, you know, it's kind of truly impossible to determine whether these are tides or transient features from just a single satellite, right? Because you don't know whether what you're seeing is temporal or spatial from a single platform. But you can get some idea by looking at neighboring days. So what here I'm doing is I'm just flipping back and forth that same picture I showed before, but on 2 consecutive days. This is February 2nd and February 3rd. So what you can see is that clearly some of these structures persist. So take a look at this strong shear layer. This is, if you map it to a location on Earth, it's here about off the east coast of the US. And this strong shear layer, it's only, like I mentioned, only several kilometers thick, seems to still be there the next day when ICON comes back around to measure it. So that was really exciting to see. And but other times these features are clearly transient. I'm looking at this shear up here, as well as there's small scale structures we often see. Here's an example on February 3rd, but it's not there on February 2nd, where there's clearly some sort of disturbance at around the 50 meter per second level that you can see continuously from 90 kilometers down in the green line all the way up to 300 kilometers in the red line. These shear layers I mentioned before, those have been seen before, most notably by chemical tracers. But what these MIGHTY data show is that they are widespread, even in daytime. They exist over thousands of kilometers horizontally, and sometimes they last for 24 hours or more. So this kind of variability is really a key science target for ICON, especially with respect to how it affects how it drives variability in the ionosphere. Okay, I'd like to say a little bit now about our efforts to validate the MIGHTY measurements using observations from the ground. So I'll go through two examples here, one using meteor radars and one using Fabry-Perot interferometers. So first with the meteor radars, for those that aren't aware, meteor radars measure winds by just taking advantage of the constant flux of meteors that impact the atmosphere every day. The plasma trail that's left behind when the meteor passes through and ablates almost immediately begins drifting with the neutral wind. And by bouncing radio waves off of it and measuring the Doppler shift, you can get some idea of the line of sight component of that wind. And by geolocating the meteor, you can understand what altitude you're measuring, as well as where it is horizontally. By averaging together enough meteors over your field of view, you can also then do an inversion to get the zonal wind, meridional wind, and sometimes the vertical wind. But you have to average for a while. The data set I'm using here, the averaging is about an hour, whereas MIGHTY flies over the site in just like a minute or 30 seconds. But so these observation modalities have very different temporal resolutions, but they have somewhat similar spatial resolutions. The vertical resolution is almost exactly the same, and the horizontal resolution is similar. The MIGHTY integration path is a little bit longer than the meteor observing's horizontal averaging function, but they're close, especially at night when the layer is thinner. So what I'll be showing today uses data from 4 of these meteor radars in the Asian sector, and for the first 5 months of the ICON science mission, there's I think it was 1,100 conjunctions with these radars. So we have a lot of data to look at here. I'll just show a couple examples. So this is 3 of those 1,100s. It's sort of like I'm showing an average case and then a good and bad case. So a 10th percentile error and a 90th percentile error, just to show the range of what we see when here. So what's shown here is a case where the MIGHTY tangent point passed within, I think this one was 80 kilometers within over the meteor radar, which is within the field of view of both of them. The colored lines here show the meteor wind profiles for, and there's 2 of them because I'm showing the averaging period before the MIGHTY conjunction and the averaging period after. And you see there's really not much change. In black is shown the MIGHTY profile. And there's a few of them shown here. The dark one is the closest approach, and then the sort of more transparent ones are the profiles measured before and after the conjunction, just to show that the wind that MIGHTY is measuring is fairly consistent. So in this case, there's a clear tidal structure with altitude that when the meteor radar falls off and loses signal, MIGHTY picks it right back up. The agreement's not always so good. Here's an average case to show that, in this case, it looks like maybe there's a little bit of an offset. And then there are cases that are quite bad where, the slopes don't even match. So, but again, this is a 90th percentile case. Those are just examples, though. I mean, we have over 1,000 conjunctions, so we can start to do some statistics. So here, each dot is a conjunction, and it's shown as the radar line of sight wind versus the MIGHTY line of sight wind. The comparison I did here was just on a sensor by sensor basis. So it asked, did MIGHTY A's line of sight cross over the radar, or did MIGHTY B's line of sight cross over the radar? So doing the comparison in terms of the line of sight wind is a little more natural for a natural comparison for the MIGHTY measurements, since MIGHTY A and B have different calibrations, and then I don't have to use the assumption that the atmosphere didn't change over those 5 to 8 minutes. So what I've done here is taken that radar profile, interpolated it in time to the MIGHTY measurement, and then interpolated it in altitude to the MIGHTY sample, and rotated the meteor's wind estimate onto the MIGHTY line of sight to compare it to the MIGHTY line of sight. And that's the best way to do an apples to apples comparison. So they don't always agree, okay? There are times when the radar measures something quite different than MIGHTY, and we ascribe that to, that's much larger than the precision of either measurement. The precision of the radar wind is reported at 1 meter per second. And the MIGHTY measurement is often precise to within like 5 meters per second. So these are above and beyond just random noise. So we ascribe those to just inherent uncertainties in each data product. For example, the meteor radar assumes that there's no vertical wind in this data set, so that introduces some error. And there's also inherent uncertainties in the space-based winds. For example, spherical asymmetry. You're looking over a long integration path, and if there's variations along that integration path in either the air glow brightness or the wind itself, that could lead to errors. So it could be inherent uncertainties, but this is also an indication of the wind energy, the wind variability at short timescales, because I mentioned the meteor radars and the MIGHTY space-based measurement have similar size averaging kernels in space, but much different temporal structures. So they measure the similar amount of energy in the wave number spectrum versus wave number, but MIGHTY sees more small-scale variability in time. Okay, but I focused a lot on the differences, but there's the one thing we were just really excited about was how good this correlation was to begin with. I mean, it's always good to see that you don't have a negative sign error, for example. So this really gave us a lot of confidence in the MIGHTY winds based on the high correlation here. There was one, I should also mention, we were excited to see the high correlation, the slope that's very near 1, it's 0.95, but most exciting for me, at least, was to see that the y-intercept was small, because that means that our zero reference was fairly accurate. All interferometers have this problem where they're very good at measuring changes in the Doppler shift, but they're very bad at determining what a what phase corresponds to a Doppler shift of 0. Because the mean additive offset between the data sets is about 5 meters per second, this really validates the zero wind reference that's used in the MIGHTY data product. Here I'm using the version 3 of the MIGHTY winds. We're going to be using this as well as other ways of determining the zero reference to make updates to this zero wind reference in future data sets. But this analysis shows that those updates will probably be quite small. One example, if you split up the data set into MIGHTY A day, MIGHTY A night, MIGHTY B day, and MIGHTY B night, you see that MIGHTY A nighttime is sort of an outlier. So we're going to be using this to help understand and fix any possible calibrations, because each one of these 4 cases actually is a different calibration. One of the exciting things about ICON is that it actually has an on-orbit maneuver to determine the zero wind. So it makes a measurement, and then 10 minutes later, it turns around and observes the same spot on Earth, but from 180 degrees aspect angle offset. So assuming that the wind hasn't changed in 10 minutes and the spacecraft velocity hasn't changed in 10 minutes, then the Doppler shift you get by those 2 measurements should be equal and opposite. And that's another way of validating our zero wind reference. There was one mystery with this comparison, though, and that's if you split the data up into day and night and make a separate scatter plot for each of those cases. You see that the nighttime looks good. The slope is near 1, the y-intercept is near 0. Great. During the day, though, the slope is notably less than 1. And that means that MIGHTY seems to measure faster winds, not more positive or more negative, but faster winds than the radars, but during day mode only. We don't understand this, and it's still under investigation. If I can speculate for a second, I think it might have to do with the flat field. For example, during the onion peeling, to interpret a MIGHTY measurement, you have to interpret a line of sight that crosses through the 300-kilometer shell and goes down to a 90-kilometer shell and back up to 300 kilometers. You have to subtract out the contributions from 300 kilometers to provide an estimate of 90 kilometers. This is the so-called Abel inversion that's part of the MIGHTY processing. If your flat field changes, or if your flat field is a small error from top to bottom, that can introduce, like, as you do that inversion, that can subtract away the wrong amount and lead to an amplification of the phase. So we're looking into that. But one thing I thought was interesting was that other space-based wind measurements have seen similar things before. So when TIDY compared to meteor radars, it found that the zonal wind climatology, I don't remember the exact details. I think it was TIDY. The zonal wind climatology from space was a little bit larger magnitude than from the ground. A similar thing was found in HARDY, and to my knowledge, those have never been resolved. So this mystery might be solved by a calibration that we're looking into, but it also might be some unknown inherent issue with the technique. So secondly, this is some work by Jonathan Makela at the University of Illinois. And this is the same idea, except instead of meteor radars, we're comparing with Fabry-Perot interferometers. These are, Fabry-Perot interferometers they're not Michelson's, but it's a similar idea. You measure the Doppler shift of the air glow. Here's one from the ground. So looking up from the ground, you measure an altitude weighted wind, because you can't resolve the altitude profile from the ground. But MIGHTY can, right? MIGHTY can actually resolve the altitude profile. So what Jonathan's done here is to take the altitude resolved wind and emission profile from MIGHTY and use that to simulate what altitude weighted wind the FPI would measure, and then compare that to the actual measurement. And that's shown as a scatter plot here on the bottom left. There's fewer conjunctions because the FPI only operates at night and only when it's clear skies. But once again, there's a high correlation and the mean offsets are small. So this was exciting because the meteor radars really only validated the green line measurements, but the red line, this FPI comparison, gave us a lot of confidence in the red line measurements as well. I should also mention there's one issue here. You know, the Fabry-Perot is also an interferometer, which means that it also has to determine zero reference independently. So the fact that the y offset is near 0 here just means that the zero reference from MIGHTY matches the zero reference from the FPIs, but it doesn't really say that either of them are correct. But the FPIs are determined by assuming that a long-term average of the vertical wind is 0, which is probably a pretty good assumption, even if the vertical wind itself is not 0 at any given time. Okay, I think I have a few minutes left, so I'll talk a little bit about some of our efforts combining MIGHTY with the IVM, which is the ion velocity meter, measures the drift of the plasma in situ, and is therefore a measure of the E cross B velocity, or so it's a measure of the electric field, really. So going back to this picture of the dynamo, for those that aren't familiar with this, the basic idea is that down low in the atmosphere, the ions and electrons collide with neutrals so often that they both basically just move with wherever the neutrals are going. And so no currents really flow if the ions and electrons are going the same velocity. Up here, in the upper thermosphere and above, the ions and electrons are basically, they're not truly collisionless, but the collisions are so rare that for the most part, ions and electrons stay on the same field line, and so very low currents flow. But in the middle, there's a region where winds can really collide with ions, but not electrons, and so they drive currents. That can set up electric fields, global electric fields that cause plasma to E cross B drift everywhere along the field line, and that's something we refer to as a dynamo. A simplified picture of this is shown here. Two equivalent ways of thinking about the problem, either as a current source or a voltage source. I prefer to think of it as a current source, but either one is perfectly valid. This, as I mentioned, you could think of as winds driving currents, which polarize the ionosphere, and that electric field, or that potential, is communicated along magnetic field lines to the F region. And up here in the F region, we're not so much interested in the current that's flowing up there, but what the electric field is across this resistor, because that will affect the E cross B drift of the plasma. And a lot of the variation in the density of the plasma from one day to the next is thought to be determined by the equilibrium in the production region of the plasma during the day, which is basically E cross B drifts pulling plasma out of the production region and populating it at high altitudes. So this is never, I mean, there's of course a lot of evidence for this, but it's never been directly observed. Okay, and the ICON observation strategy was really built to look at this. This is a representation of a magnetic equator crossing of ICON. So when the spacecraft actually crosses the magnetic equator, the black dots are ICON's location. This sort of data curtain down here, the color represents the wind observations made by MIGHTY down at the tangent point. This is obviously not to scale. The vertical coordinate is stretched considerably. The green lines are the magnetic field lines, so the equator crossing happens right about here. And you can see there's, during this time, there's a point where ICON is making a measurement here of the electric field at the same, almost exactly the same time that you measure the winds down in the dynamo region on the foot point of the same field line. This is actually kind of a unique geometrical curiosity, I guess, that if you have a dipole field line and you look out at 45 degrees from the magnetic equator, the tangent point profile actually lines up exactly with the field line. In practice, it never works out exactly perfectly, but close enough. So this gives us a way to really understand the lower thermospheric wind drivers down here at the foot point of the field line and how they impact the plasma drift up here at the spacecraft. So you remember the large shears I showed in the MIGHTY winds. What those really show is that it's not really correct to think of this as such a simple circuit that I showed before. It's not like there's a dynamo region that has a battery. It's almost like you have a dynamo region where you have a lot of batteries in parallel, and sometimes you put a battery in the wrong way because the current being driven at one altitude is canceled out by a current at another altitude. So in other words, the wind-driven dynamo is many times inefficient in that the kinetic energy in the wind is not going efficiently into electromagnetic energy, but rather being dissipated locally, either locally or at different regions horizontally spread out. One of the things that I think is really exciting about ICON is actually measures that if you assume you know the conductivity, which is fairly well known during the day, it actually measures the current. So this is the conductivity shown as Peterson component and Hall component. The conductivity times U cross B is the wind-driven current, and that's shown here. So here's a wind profile, and then here's the wind-driven current. So, and then when you add IVM, you can get the electric field on that same field line and understand the total wind-driven current and actually resolve it in altitudes. And then you do this at one place, but you can leverage the global coverage of ICON to understand the distribution of the current profiles over longitudes, local times, etc. This also shows that the important quantity, if you want to try to understand the dynamo, is not the wind, but the conductivity weighted wind. Okay, what's the total impact of the batteries that you've lined up in parallel? So the dynamo is global and complex, and in general, the wind at one place can affect the electric field somewhere else. But you can get a very simple, simplified version of it in certain situations. So for this result, what I'm just going to be showing is near local noon. So you could this is the SQ current system, the average solar quiet current system in the ionosphere. The meridional current is negligible near local noon, which means that the zonal current must be constant, okay, by current conservation. Near equinox, the northern and southern conductances are similar, so you don't expect one hemisphere to be driving in a dominant way. So here we'll just focus on the northern hemisphere observations. Mighty's looking for the most part northward. And during quiet times, we can really isolate the effect of the lower atmosphere because the high latitude potential really doesn't affect the currents. So under this approximation, you can write an equation for the zonal current. And in this equation, it shows has two contributions, one from the electric field. Here I've just written it in terms of the plasma drift because that's an ICON observable. And then wind-driven currents as well. In general, because there's a Peterson and Hall component, all different wind components can drive a zonal current. So under this assumption that the zonal current is constant, you should see an anti-correlation between the plasma drifts and the winds. And that's exactly what we see. Here is the each of these small dotted lines is one of the wind components, the Hall-weighted zonal wind, Pedersen-weighted meridional wind, etc. The black line is the combination of those components as shown here. And the blue line is a completely different measurement. That's from the IVM. That's the electric field, the vertical plasma drift. Just to show this a little better, what I've done is just taken the black line and flipped it upside down and removed the zonal mean to show that there's a clear relationship between the lower thermospheric wind drivers and the electric field, the plasma drift, that has a direct contribution to the plasma density. So this represents the first direct detection of the dynamo in action in terms of the longitudinal variability, and opens up a lot of opportunities for future studies to look at how this changes, latitude, longitude, local time, etc. Okay, so in conclusion, I'll leave you with this. We're really excited about the opportunities that Mighty and the other instruments on ICON bring for the community. Mighty is not the first wind sensor. There's Hardy, Windy, Tidy, but and of course Mighty takes advantage of what I mentioned. The continuous coverage, no duty cycling. But more exciting for me is that Mighty exists on the same platform with these other instruments to really understand all the mechanisms that can create ionospheric variability. So we now have several months of data that's available to the public. UGO's website here. So I invite you to crack that open and let us know if you have any questions with that. And with that, I'll end and take questions. Thank you.
Okay, thank you, Brian. Good to see some of these new results. If anyone has a question, you can either type it in the chat and I can read it to Brian, or we can try to somewhat negotiate people speaking and asking the question directly. So I do have one question. If everyone is thinking of if they have a question. You show a lot of these smaller scale structures. Do you know what is the kind of spatial and temporal resolution that can be resolved from the observation?
Yeah, so the temporal resolution of Mighty is 30 seconds during the day and 60 seconds at night. There's a couple of things that contribute or that degrade our ability to resolve spatially. One is just our field of view. Any given exposure time is something like 200 kilometers wide on the tangent point. Also, the smearing during our exposure is about 250 kilometers during the day and 500 kilometers at night. And there's also an integration along the line of sight. And that's pretty difficult to quantify because the onion peeling can cause errors if there's spherical asymmetries. But that's of the order of 500 kilometers.
And Dan asked a question in the chat here. Is there an effort to tie the variability seen in the thermosphere winds to variability in the troposphere?
Yes. Our first goal is, of course, once you know the variability, you measure the variability directly with the Mighty at 90 kilometers. That is the wind that affects the ionosphere higher up. But of course, we're interested in understanding where that variability comes from below. There's an effort. Part of the ICON mission is a modeling effort that I'm sure a lot of people in the audience know much better than me about. But that does understand or aims to use realistic variability from below through reanalysis to drive models that can propagate that to the altitudes we observe.
And then there's another question from Han Lee. Have you calculated the correlation between the ion drift and the measured neutral winds?
Yeah, for the case I showed, the correlation was about 0.6, I think it was. We actually get a plot like that every precession. I think it's every precession cycle, and it's not always the same. So that's something we're trying to understand. But it's of that order, 0.5 to 0.8. So clearly, I forgot to mention, it's not a perfect correlation, of course. The reason it's not perfect is probably because these assumptions we made here are not always perfectly satisfied, and also because the dynamo is not the only thing contributing to the drift variability.
There's another question from Sue. How much is the impact of the South American anomaly on Mighty measurement? And are you able to get winds in most of South America?
It's you can get a feel for it from this plot I showed earlier. Let's see, where is it? So it's a significant bite out here. This bite out that I'm showing here is probably a little bit conservative. So when we go through future data product releases, this bite out will get a little bit smaller. But if you're trying to do any comparisons with ground-based instruments in South America, you got to be really careful.
And there's a follow-up from Han Lee about the correlation. He was wondering, how does the correlation depend on local time?
We haven't looked at that in detail. Right now we've been focusing on local noon because that's a simplified case. But of course, we're interested in looking at different local times. But then you want, if you're going to do that, you want to zoom out though, because at other local times you get a lot more non-local driving. So, for example, the winds at the terminators can cause electric field variability somewhere else because the dynamo is it's a coupled circuit. It's not this simple circuit that I showed before. It's a bunch of circuits all connected to each other. But that's certainly something we're looking at.
Thanks. And there's another question from Shugang. Is the variability seen in thermosphere wind also tied to geomagnetic activity? And even though it is quiet time, there's still some levels of geomagnetic activity going on.
Yeah, thanks for asking that. That's actually Icon science question number 3. We've been pretty fortunate, actually, that it's been so quiet during the first several months of the mission, because that's allowed us to really isolate the variability from below. But there have been a couple storms, as you know, maybe not big storms, but we have seen definite changes in the thermospheric winds. You know, the big traveling atmospheric disturbances that propagate from the high latitudes. You could just watch the meridional wind surge goes far southward in mighty data from one orbit, and then you come around to the next orbit and you see it again. So we have a couple examples of that that we see, and that you could see if you open the data.
Thank you. So another question from Gang Lu. At which altitude are you comparing the winds with the ion drift shown in this plot that you have up right now?
Yeah, I think I forgot to mention that. So the ion drift's measured at the satellite, which is around 600 kilometers. It's an in situ measurement. The winds are measured from 90 to 300 kilometers. And for this plot, the plot that I showed, what I've done is computed the conductivity weighted wind. So this is really just looking at the part of the wind that is actually driving currents in the field line integrated sense. And the winds at other altitudes are really just driving local currents that aren't really polarizing the ionosphere. So this is 600 kilometers and a conductivity altitude weighted wind.
And she had a follow-up question of how do you derive the conductances?
So for this, I just used MSIS IRI. During the day, it's fairly well understood. It's in this sort of photochemical equilibrium. During the night, it's of course much more complicated. But here it's a climatological model with the photochemical, with the cross sections identical to the ones that are used in the TIE GCM.
Thank you. All right, I think that maybe is all of the questions. So thank you, Brian, for a very nice presentation. I think everyone was quite pleased to see these new data. So thank you again.